my name is Kenshin and I'm very honored to be here to present my fifth place solution for the Kaggle TPU graphs or fast or slow competition. So here's today's agenda, and let me start from my background. So I finished my master course of computer science 3 years ago, where I basically studied machine learning, and I am currently working as a software engineer at Preferred Networks. And here's the summary of my solution for the competition. And I basically use 3-layer graph neural network based on graph search. And what I think was important, what I think was the most important in my solution was to train a large graph neural network on a whole data set, including, 4 kinds of layout data set, and also a tile data set. So here, because tile data set, for tile data set, almost all participants scored almost perfect score. So the layered data set was important in the competition. And even for the layered data set, I included tile data set for training, and it enhanced our performance. And it took 1.5 days for training in 4X NVIDIA V100. And for feature selection, I basically used all the features except for ones that are constant across the whole data. And I apply log scale transformation for some input, and it was important because, for some features, they are like very, the distribution was like something like 1, 2, 3, 100, 1,000, 10,000 or something like that. So I made it close to like normally distributed or something. And also for some opcode, there are limited number of opcodes in the data. So I use the same opcode embedding for unary operations such as abscissa, cosine, etc. But I'm not sure if it was the right thing. Like, I was not sure if it can be regarded as the same runtime in the TPU. And this is my training method. So I used Adam W optimizer to train a model with a cosine annealing learning rate scheduler, and I basically used the pairwise hinge loss, which was kind of a ranking loss, and I combined the two pairwise hinge loss. So the first one is the basic one. So I think I first need to explain how I sample graphs and configs in each batch. So I sampled a few graphs in a batch, which is basically like 4 or 8. And for each graph, I also sampled a few configs like 8 or 16 configs for each graph. So we have like a multiple graphs in a batch, and for each graph we have also multiple configs. And the first loss is the mean pairwise hinge loss among configurations by each graph. So for the first one, we basically compare configuration among configurations in the same graph. And the second one was the pairwise hinge loss among all samples in a batch. So here we compare different graphs, which was actually not a main target of this competition, because for the scoring metrics, we are for the scoring metrics, they only compare the configurations in the same graph, but including this as a loss function enhance the Kendall Tau score for each graph. So I think this was because the model can model can also learn some basic information, like larger graphs have a longer runtime, or like the graphs with the large tensor shape should have a longer runtime. And because of this, I used full graphs for training, because if we if we prune some nodes, like the comparison of different graphs can be unfair. So basically, this was my training methods. And here is the detail of my model. So as I explained, I thought as I explained, my most important point was to train a large graph neural network model using the whole data set with augmentation. So with this setting, I mean using the whole data set with augmentation, the larger mid-channel size was significantly better than the smaller mid-channel size, like 256. But I actually realized this on last few days, and I couldn't finish the whole training before the competition finished. So my score enhanced significantly after finishing the competition. And for the augmentation, I I didn't know what kind of augmentation works in graph neural network training, but I figured out drop edge, which randomly drop edges during training and use the whole edges during the inference phase, which that significantly enhance the performance. So with this setting, was my best training setting. And I also implemented different architecture, which uses dimension invariant transformer. And I explained about this in the discussion in detail, but I couldn't make it work for the layout dataset, and that worked only for the tile dataset. So it was not important in the perspective of the competition score, because I mean, tile data set. For tile data set, we scored already like almost perfect for that data set. So for the simple model, actually, I couldn't finish training this model during the competition, but after finishing the whole training of the model, in the setting I explained earlier, the single model could actually achieve first place score, and also ensemble of 2Cs scored even better. So that was the end of my presentation.